Thank you. Thank you to the organizers for inviting me, giving me a chance to speak. About a decade ago, I was a postdoc here at the KGRC with Katja. It's very nice to be back. This is, as it says, joint work with Noam Greenberg and Isabella Scott. There are three things in the title: derivatives, antiderivatives, and priority arguments. I'm mostly going to be speaking about the first two. I will have a very little to say about priority arguments. Yes? Oh, is the microphone not?
It's not a microphone.
It's not a microphone. It's not a microphone. Oh, it's just a recording. Okay, sorry.
No, I think it is a microphone. We don't know how to use it.
Okay, I'll just be louder. Sorry.
Can you start over?
No. Despite saying graphs, I'm actually going to start with linear orders. So here, K will be a linear order. I'm using K instead of L because in a little bit I'll talk about Gödel's L, and I didn't want collision of notation. Let's talk about the Hausdorff derivative. So I'm going to define an equivalence relation. 2 points are equivalent in my linear order if there are only finitely many points in between. And we can iterate this. So that's the level 1 equivalence relation. Successor relation, two things are equivalent at alpha plus 1 if there are only finitely many alpha equivalence classes in between them. And at limits, we take unions. So two things are lambda equivalent if they're alpha equivalent for some alpha less than lambda. And then we define the Hausdorff derivative as the quotient. So the equivalence classes are convex, you can show, and therefore the quotient is a linear order. The computability of this, if it takes 2 jumps to compute the Hausdorff derivative, and this iterates. So there's a bit of a difference depending on whether alpha is finite or infinite. If alpha is finite, then computing the alpha derivative takes 2 alpha many jumps. If alpha is infinite, then it takes 2 alpha plus 1. And the reason is this sum alpha, that's a quantifier. That extra quantifier right there is the plus 1. I could have unified this using sigma notation. I could have written sigma 0, 2 alpha plus 1, but I actually want to emphasize this difference. And then we can do a converse. So this is a result by Ash and Watnick. If I have a linear order which is computable at the correct level, then I can take an antiderivative. So multiplying by z to the alpha is an antiderivative. If I multiply by z to the alpha and then I take the alpha derivative, I get back what I started with. And taking the alpha derivative required 2 alpha or 2 alpha plus 1 jumps, and multiplying by z to the alpha removes 2 alpha or 2 alpha plus 1 jumps, finite or infinite. And you could replace z to the alpha with omega to the alpha, and it would all still be true. So this is showing, just like in calculus, that antiderivatives are not unique. This is all non-uniform. The amount of non-uniformity required in the z to the alpha is very small. You only need to non-uniformly know whether or not k is empty. Slight amount. Omega to the alpha, you need a little bit more non-uniformity. You need to know whether or not k has a least element. Right, so that's this result in standard countable computability theory. Now I want to talk about uncountable computability theory. We've seen alpha recursion theory in a few talks already, but very briefly. Take a regular cardinal kappa, uncountable. Alpha recursion theory works for more than just this, but you don't need a cardinal, you don't need regularity, but I want to restrict my attention here because I'm going to be doing computable model theory, and a regular uncountable cardinal keeps the computability nice, and so you can focus on the model theory. So we're working in L kappa. A subset of L kappa is going to be kappa CE if it's sigma 1 definable in L kappa. And once I know what CE means, I know what computable means. It's computable if both you and your complement are CE. I know what Turing reductions are because I have a CE set of axioms. Turing reductions get me Turing degrees. I get the usual theory. So now I want to take Hausdorff derivatives and these antiderivatives and look at them in kappa computability theory. So we defined in normal countable computability theory, we defined the equivalence relation. Two things are equivalent if there are finitely many points in between them. Now in kappa, the natural thing is to say that 2 points are equivalent if there are fewer than kappa many points. So that's my equivalence relation. I iterate in the exact same way. And then I get Hausdorff derivatives. And it still takes 2 jumps to compute the Hausdorff derivative. The problem is there's no antiderivative. Remember, the Hausdorff derivative is a quotient. So an antiderivative, we'd want, or there is an antiderivative, but it doesn't play nicely with computability. There's no antiderivative that plays nicely with computability. We want something whose quotient is the original linear order, and there's no way to do that while removing 2 jumps. You give me any Turing degree, I can find the linear order in that Turing degree such that no matter what sort of antiderivative I take, anything that has n as a quotient, it's still above, in or above that Turing degree. I can't remove 2 jumps by taking it, which might say, okay, we're just out of luck. And because this is just for any sort of quotient, changing the equivalence relation isn't going to fix this. But it turns out really what this is saying is that we shouldn't be looking at quotients. Our derivatives should not be quotients. Instead, let's make our derivatives substructures. So I think of this as a kind of Cantor-Bendixson derivative. If you define the right topology, it literally is the Cantor-Bendixson derivative. I've got a linear order. I'm going to take the subset consisting of all points that have kappa cofinality. So I have a point, I look at the linear order to its left, I say, what's the cofinality of that initial segment? I keep the ones that have cofinality kappa, throw away everything else. Again, this is a substructure, not a quotient. And then I iterate. So this is successor steps, and at limit steps, I take intersections. And again, it requires 2 jumps. So in normal countable computability theory, we had this dichotomy between finite and infinite ordinals. Here, it turns out there's a little bit more going on. I need to ask, if I've got an alpha, what is the last limit ordinal? Less than or equal to alpha. And it's either long, meaning it has cofinality kappa, or it's short, meaning it has cofinality less than kappa. It's only at the long limit ordinals that we get the +1. Finite things, it takes 2 alpha many jumps. If you're finitely far above a limit ordinal with small cofinality, then again, it just takes 2 alpha many jumps. If you're finitely far above something of big cofinality, then that's where the +1 comes from. How about an antiderivative? The way we're going to define the antiderivative is if I've got a linear order, I'm going to look at every initial segment with small cofinality. And in each of those for each of those initial segments, I'm going to insert a copy of kappa immediately after it. So remember, the derivative is a substructure, so the antiderivative should be a superstructure. So I'm just adding more points. This includes inserting one at the very beginning for the empty initial segment, and if the linear order has small cofinality, then I'll also stick one at the end. This is an antiderivative. If I do this integral and then take the derivative, I get back what I started with, because I have a point x, look at the initial segment to its left in the original linear order. If that was small cofinality, then I inserted a kappa, and suddenly, in this bigger linear order, uncountable, the cofinality is kappa. If it was big cofinality, then I didn't insert anything, but it was big cofinality. So the old points stick around when I take the derivative. And the new points are all inside here. Everybody in kappa has cofinality less than kappa. They all go away. And this does behave computably nicely. It removes 2 jumps. I spoke about this result a decade ago. Noam and I thought we had not just this, but we had the iteration of this. Turns out we hadn't worked out all the details, and we didn't quite have the definition of the iteration correct. I'll say more about how to iterate antiderivatives when I get to graphs, but and also that time we were only working for computable ordinals. Now this is still work in progress, but we've sketched an argument and we're busy writing it up. Now we think we can do this for hyperarithmetic ordinals, and that's a distinction, computable versus hyperarithmetic ordinals, that I'll say more about later. Okay, so let's go back to normal computability theory, but with this idea that our derivatives shouldn't be quotients, they should be substructures. But that's the approach I want to study. So I'm just going to do what I did before and just replace kappa with omega. Normal computability theory, I'm going to say, keep the points whose initial segments have cofinality omega, throw away the points that have smaller cofinality, which, if you unpack that, that means throw away successor points and also throw away the least point. Keep limit points. And then the antiderivative, I'm going to do the same thing, except instead of inserting a copy of kappa, I'm going to insert a copy of omega. Again, I haven't said how to iterate this, but there's a way to iterate this, and it behaves nicely. It works exactly as we'd expect to undo the differentiation. If alpha is finite, then taking the alpha step integral removes 2 alpha many jumps, and if alpha is infinite, it removes 2 alpha plus 1. And unlike the Watnick, this is uniform. So then we had this approach of make the derivative a substructure, not a quotient, and in particular, the points we keep are points that are exhibiting some infinite behavior, limit points in the case of linear orders. And we thought, well, can we try this in other classes of structures? And so we looked at graphs. Turns out linear orders are hard, which is perhaps a surprise given that from a computability perspective, they're not universal, and graphs are universal. And yet somehow graphs are easier. So define the derivative of a graph. Okay, we want to keep the points that have the vertices that have some infinite behavior, and the natural choice is degree. So we're going to keep the points of infinite degree and throw away the points of finite degree. And here I mean the full subgraph, so keep every edge that you're able to keep. For me, a graph is a first-order structure where the vertices are elements and there's an edge relation in the language. Substructure, of course, you keep every edge that you can keep. Again, it's the same iteration. This is how you do successor steps, and at limit steps, you take intersections. And it still requires the same complexity to compute the derivative. It takes 2 jumps to compute the derivative, and at limit stages, this extra plus 1 shows up and sticks around because it takes 2 jumps to compute the next derivative. Okay, how about an antiderivative? So a natural guess got my graph G. I need a superstructure in which every vertex of G has infinite degree. So a natural thing would be to just say, oh, give it infinite degree like this. I'll just add a whole bunch of otherwise isolated vertices that are attached to each vertex. That is an antiderivative in the sense that if I take the derivative, I get back my original graph. But it doesn't play nicely with computability theory. The problem is all of these vertices have degree 1, so all the old new vertices have degree 1, all the old vertices have degree bigger than 1. That makes the old graph G is very easily definable inside the new graph, which means that you can find a graph such that taking the antiderivative doesn't remove any complexity, doesn't make things easier. In the case of linear orders, we had this result that there's a linear order where if you take a quotient, it doesn't remove complexity, or you take something whose quotient is that linear order, it doesn't remove complexity. And that told us that we needed to change derivatives entirely. This is not that general. This is not saying that there's a problem with the derivative, just that there's a problem with this particular antiderivative. So we use a different antiderivative. The way we're going to build our antiderivative, we're not just going to attach individual vertices, we're going to attach finite graphs. I want to take a finite graph and I want to attach it using only finitely many edges. And I want to do this in every possible way. So every finite graph and every way of attaching using finitely many edges, I'm going to do that. I'm going to add that. Notice that if H is a finite graph, then the disjoint union of H with itself is another finite graph. So not only am I attaching one copy of H, I'm attaching infinitely many copies of H, which is really what I wanted, but it's easier to state this way. And this does behave nicely. It does remove 2 jumps to take the integral. And the reason is, these finite graphs let you do garbage collection. You're doing a priority argument to try to build this. You're approximating G because G is not computable. You put some vertices down thinking that they're in G, and then you realize that you were wrong. They're not in G. So you've made a finite chunk of mistakes. You say, well, that's okay. That finite chunk is just some finite graph that was supposed to be there anyway. I'm okay. How do we iterate this? So one guess would be to say, okay, I know how to do it twice. I just do it and then do it again, or 3 times. But how do I do it omega many times? Well, you might notice that each one's a superstructure. The graph is inside the integral, inside the double integral, etc. You might just think, take unions at limits. The problem is this gives you the random graph. And that's bad for 2 reasons. One, the derivative of the random graph is the random graph, so I'm not going to be able to get back G. And in fact, if I'm getting the random graph for every graph, it doesn't matter what G I started with, I'm always getting the random graph. I've lost the information about G. Of course, I can't get back G by taking it. So this is not the right way to iterate. And the problem is that this omega chain, I've got an omega chain here because I'm doing an omega limit, it's going the wrong direction. It's going up, and we need it to go down. I'm going to give a kind of category theory flavored description of the antiderivative. So the antiderivative will be a graph M. I was running out of letters for graphs. I can start taking derivatives of M. I can take the first derivative, the second derivative, all the way up to level alpha. And at level alpha, I want to get back my original graph G. And at every successor step, I want what I have at this step to be the integral of what I have at the next step. So now, my sequence of length omega, if I'm just going up to length omega, height omega, my sequence is getting smaller as I go up, not bigger. So that's why I'm saying the sequence was going the wrong direction. There's also a minimality condition, which is not hard. If you're interested, we can discuss it later. But the minimality condition is necessary for uniqueness. I just have anything that satisfies this, it will be an antiderivative, but it won't necessarily be unique. But I've said the antiderivative is the graph that satisfies this. It's not obvious that such a thing exists, but it does, and it's unique. And the antiderivative removes complexity. So if my graph was 2 alpha computable and I take the alpha antiderivative, alpha is finite, then I get a computable graph. So I remove 2 alpha jumps, or if alpha is infinite, it removes 2 alpha plus 1 jumps. Okay, so now let's go back to kappa computability theory and say, can we do this in kappa? I need to say a bit about ordinals. In normal computability theory, computable ordinals and hyperarithmetic ordinals are the same thing, but that's not the case in uncountable computability theory. If you look at the least non-computable ordinal, it will be zero-jump computable. So we could just restrict our attention to computable ordinals, but we'd like to go further. So we're going to define a system of notations for hyperarithmetic ordinals, and this will be like Kleene-Zhou. But in Kleene-Zhou, you say, if I've got a computable function that gives me an increasing sequence of notations, then there's a notation for the supremum. Here, I say, if I've got a functional, a Turing functional, and I've got some notation to use as an oracle, so H said this is the jump at level A. If I've got some notation to use as an oracle, then it gives me an increasing sequence of notations starting from that notation that I use as my oracle. Then I want to add a notation for the supremum. So we're closing not just under computable functions, but under hyperarithmetic functions. We developed this system of notations. It works nicely. You've got Spector's theorem about the jump. The degree of the jump does not depend on the notation. You get at basically, it looks like what happens with normal computability theory. Now I want to define the derivative. In the countable world, I said infinite degree of, since it's countable, that means degree is aleph naught. Here we've got kappa, so I'm going to say I want the vertices of degree kappa. Throw away everything whose degree is smaller. Iterate in the exact same way. This is the successor step at limits take intersections. And again, computing the derivative is as we saw before. There's an extra +1 that shows up when the last limit ordinal was long, when it had cofinality kappa. And when the last limit ordinal was small, or if it's finite, so there is no last limit ordinal, then you don't get this extra +1. Okay, so now we want an antiderivative. And again, I'm just going to take omega and replace omega with kappa. So instead of finite graphs, I look at graphs of size less than kappa. Instead of finitely many edges, I look at fewer than kappa many edges. Any way of attaching such a graph, I do that. Then I iterate, no change to the iteration, same thing. Yeah. Yeah, this is all in L. So.
Oh, it's in L.
Yeah, yes. If we were working outside of L, we'd have to worry about more. okay, we don't quite have the optimal result for this. So we want it to be that taking the alpha integral removes the correct number of jumps. And if alpha is a computable ordinal, yes, no problem. If alpha is a hyperarithmetic ordinal, we can't quite do that. And I'm not saying it can't be done, just I'm saying we don't know how to do that. So what it should be is, again, if the last limit has large cofinality, then you remove 2 alpha plus 1 many jumps. And if the last limit has small cofinality, you remove 2 alpha many jumps. We can't quite make this work in this second case where the last limit has large cofinality. We can only remove 2 alpha many jumps no matter what. We can't quite get 2 alpha plus 1 in the case where we should get 2 alpha plus 1. This is for hyperarithmetic ordinals. Again, computable ordinals, no problem.
How you iterate?
So it's this picture again. So the antiderivative is some graph M with the property that if you take alpha many derivatives, you get G. But if I take, I can take fewer than alpha many derivatives, and I get this whole sequence of graphs. And at every successor step, it should be the one-step integral between these two. So this should be the one-step integral of that. And there's a minimality condition that I haven't. Sure. If I've got, yeah, so let's, alpha equals 2, say, and G is that. So then alpha equals, and so at level 1, this is what I want at level 2. At level 1, I want basically to take every finite, or well, finite if I'm in omega computability, less than kappa if I'm in kappa computability, but I take every small graph, and I only want a small number of attachments. Well, there's only one vertex to attach to, so problem. Any way of attaching a small graph, so any subset of the possible edges, I do that. And then at level 0, I say, okay, I've got that. I've got this already because I'm making a superstructure. So I've got this, and then I say, what's every way of attaching a small graph? So maybe I'll use a different color. I could do a small graph here that's attached to a few of those, and maybe it's attached there, and maybe it's attached there and there, but it should still be a small number of edges between this graph and the old stuff. And I keep doing that. I find a different small graph and I attach it. That's 2. If alpha is omega, so...
In general case, can you take
that is the way we prove existence, is we have this concrete definition, which is it's a labeled tree where vertices are labeled by triples. A graph, a point from the graph, and an ordinal. As you go up the tree, the ordinals need to strictly increase. If the ordinal is the top is alpha, then this should be the original graph G. Otherwise, it should be a finite graph or a less than kappa size graph. And the edges of the tree should be labeled with a subset of H. And the idea is this vertex, this node of the tree, represents the vertex X, which was added as a part of H at this level to be connected in the way the edges say that they should be. Well, if I'm just trying to prove existence, then I'm not actually doing any computability at all. This is just ordinals. But this definition makes sense for any ordinal. So I don't build it using the tree. I build it using a priority argument. So the tree is to prove, or not a single tree, a family of trees, is the existence proof that it actually exists, but that's just a classical proof, no computability involved. But yeah, so the question is, if alpha equals omega, what does it look like? At the omega level, I want to have a singleton. Everybody down here should be a superstructure. So I've got this distinguished singleton that distinguished, at least to me, singleton that exists at every level. And each level I've done this again. I've attached finitely any kind of finite graph that I could, I've attached it. And they should be substructures, so at every step I take the derivative to get to the next one. And if I take the intersection, all I get is the singleton. Does that help?
It was a spec, right? Each of these graphs.
Yeah. Yes. Generally we would expect. Yeah. So they should all be isomorphic. The graph that I get at level beta should be isomorphic to the alpha minus beta integral, which if alpha is a limit ordinal, beta is small, say finite, or so if alpha is infinite, beta is, if beta is much smaller than alpha, then this is going to be the same thing, kind of no matter what beta is. Yeah, for a while I do expect to get the same thing.
But you said you need to what? Can you build this plan by taking the?
But if I want a computable copy, I need a priority. Right, if I just want a classical copy, then we have this explicit, or you can just kind of go along and you just kind of do a, say, what are my conditions are that for every finite subset I have to attach, and every finite graph I have to attach this finite subgraph in this way, and just kind of go through all the conditions one at a time and well order it and build it. It's just, you need the priority argument if you want to drop the computability. To make it nicer, computably. Other questions? Let me say a little bit about the proof techniques. Again, this is if I want to make a nice copy of the antiderivative. You need some way of doing long iterations of priority arguments, some sort of worker argument. Ash had his meta theorem. We favor Antonio's true stages method, which we had to develop for hyperarithmetic ordinals and capital computability. Why are we missing this +1? The way you get the +1 if you're doing a true stages priority argument is you use a technique called shifted true stages, which Antonio implemented in his version in the countable, and then we were able to do this in kappa computability for computable ordinals. But for hyperarithmetic ordinals, we're not quite sure how to do it. And there are a few avenues we haven't finished pursuing, so maybe it will pop out. But at the moment, we're not quite clear how to get it, which is why we don't have this, which is why we're missing the +1 non-computable ordinals in kappa computability. Okay, so now we've got this general approach of my derivative should be a substructure based on keep the elements that have some infinite behavior and throw away everything else. We've done it for graphs and linear orders. Can we do it for other classes of structures? So we've decided to try trees. Here, trees for me are in the language of directed graphs. So a node has an edge pointing to its parent. The natural thing would be to say, throw away the vertices with finitely many children, keep the vertices with infinitely many children. That doesn't give you a tree because that's not downward closed. That gives you a forest. And I'll talk about forests in a second. But if you want a tree, you need something downward closed. You want the derivative to be a tree. So instead of looking at just the children, we look at all the descendants. If a vertex has infinitely many descendants in the tree, then keep it. Infinitely many if we're doing countable computability, kappa many if we're doing kappa computability. Now I need an antiderivative. My antiderivative, I'm going to might be infinite branching or finite branching. What I'm going to do is, to every vertex of my original tree, I'm going to attach a copy of every finite tree, finite in omega computability, less than size kappa in kappa computability. I mean, every small tree, I'm going to attach a copy there. In fact, I'm going to have to attach infinitely many copies. Really, for the graphs, I wanted infinitely many copies of every small graph. But I got that for free. You can't make the same argument here. So I had to explicitly say attach infinitely many copies at every place that you can. So the iteration is exactly the same as graphs. All the graph results hold for trees. In fact, they hold by the same proofs. I took the write-up for graphs, and I did some find replaces, and I deleted some stuff that wasn't necessary anymore, and I had the write-up for trees. So in fact, it's the same arguments, in fact, slightly easier. Forests. So forests, I could use, so forests are I'm thinking about these the same way I thought about trees. I've, again, directed graphs where a vertex points at its parent. I want to have roots distinguished. So maybe I have a unary predicate, or maybe roots point to themselves. Somehow roots are distinguished. I could use the same derivative I just used for trees. That would work. But since we had this other candidate that didn't work for trees, let's think about that. Here, keep the things which have a large number of children, throw away the things which have a small number of children. Because if I do children for trees, that's not a downward closed set, so the derivative won't be a tree. If I'm doing trees, I want the derivative to be a tree. Whereas I'm doing forests, I don't worry about that. But I could do descendants here, and it would also work. I'm going to do the exact same antiderivative, except I also need just free-floating tree. Every finite tree needs to be free. I have free-floating copies that aren't attached to anything. Otherwise, it's the exact same antiderivative. Iterate in the exact same way as before. Everything still works. So presumably, there will be other classes that one could do this sort of argument for. Not Boolean algebras. The problem is that Boolean algebras have very few definable subsets. Pretty much, if I start with a small Boolean algebra, say the Boolean algebra of, I don't know, 8 elements, and I decide I want an antiderivative, which should be a superstructure, since the derivative should be definable, I should have an 8-element subalgebra sitting inside of it, and Boolean algebras don't do that. They don't have these fixed elements, except you can do a little bit with atoms, but that doesn't have the right complexity. So it doesn't seem to work for Boolean algebras, so it's not going to work for everything. And notably, Hausdorff derivative does work for Boolean algebras, so quotients work fine for Boolean algebras, substructures don't. But presumably, there are other structures where this approach would work as well. I'm suspicious about reduced abelian p groups. you.